The other application is exponential decay. Exponential decay and what's known as half-life. The half-life is like your interest rate. The half-life, let's talk about that definition. The half-life of, this looks like at, the half-life of a radioactive element is the time required for the initial or present amount to decay to half its original value. This is pretty much the the cricket jumping to the other side of the shoebox for those of you that saw that video or remember that conversation. So let's look at an example. So we will use the same model as the compound, the continuously, cannot spell at all today, compounded interest model. The continually compounded interest model was A equals P e to the RT. The book uses a slightly different formula. They say, this is A of T is equal to A naught E to the KT. So they use different letters, but don't let them fool you. P is A naught. It's the initial amount, and the interest rate and the decay rate are R versus K. So typically for interest, R is greater than 0. And for decay, K, not R, come on, K is less than 0. As we discussed when we talked about graphing exponential functions. So let's take a look at an example. Let's see here. Phosphorus (32) used in agriculture, probably fertilizer bombs, has an initial amount of 2 milligrams and a half-life of 14 days. A. Find the decay constant K. Round to 4 decimal places. Accurate to 4 decimals. B. Determine the decay function. A of T, this is the amount present after T days. And C, determine the amount of time it takes for 90% of the sample to decay. I'm going to actually move this down to it's all on one page. That way when I put it on a PDF later, it won't be so broken up. Okay, let's start with A. Let's do this in a different color. A. Before we go any further, I just want to say I see some really interesting things when people do this problem, and there's a really obvious noob mistake that people make. At no point anywhere in this problem will we be using the number 32. That is just a numerical value name for the isotope of phosphorus, and it has nothing to do with our calculation. So I see a lot of students, they don't know what to do, so they just throw 32 in there somewhere. So let's start off with what we're talking about. We're going to start off with our generic formula. A of T is equal to A naught E to the KT. And if the half-life is 14 days, we're going to do this, first of all, we're going to do this entire problem in days. So everything in terms of the amount of time it takes is going to be measured in days. If the half-life is 14 days, that means that we could do one of two things here. Either we can actually plug in the fact that we have 2 milligrams to start with, or if we start with some general amount, A naught, this is the initial amount, we have E to the K times 14 days. And I want to know what the half-life is. That means in 14 days, whatever we started with, we'll be left with exactly half of what we started with. So half of initial. And this is the time for the half-life. So we have a simple equation here. This is 1/2 A naught is equal to A naught E to the K times 14. And to isolate our exponential, we'll divide both sides by A naught. And we'll see here that actually it doesn't matter how much you start with. In exponential decay, when you talk about a half-life, it takes the same amount of time for this isotope to decay down to 1/2 if you start out with 1,000 grams, a kiloton, or a couple of micrograms. It's going to take the same amount of time because it's independent of scale. Anyway, we'll take the natural log of both sides. The natural log of 1/2 is equal to K times 14, or K is equal to the natural log of 1/2 over 14. That is to say, in general, the decay rate K is equal to 1/2 over the half-life. And for those of you that play video games, half-life is pretty fun. And the symbol for half-life is lambda. So we might write the natural log of 1/2 over lambda, where here lambda is 14. Anyway, not a big deal. Anybody know what I'm talking about? Video games, half-life? It's another older one, I guess. It's not Fortnite, so nobody knows what I'm talking about. That's okay. Let's move on. So we want that accurate to 4 decimal places. So K equal to, the natural log of 1/2 over 14 is approximately Natural log of 0.5 divided by 14 is about negative 0.0495. 0. And you'll note that here, K is in fact less than 0 because it is decay. Okay, that's great. Then for part B, determine the decay function, which is the amount present after t days. Well, for part B, that's just A of t is equal to A naught e to the kt, where A naught is our initial amount, 2, and we have our decay rate, negative 0.4950 t. That looks weird to have that 0 on the end. I'm just going to get rid of it. Where A naught is our initial amount and K is our decay rate. For part C, finally, they say how long until 90% has decayed away? Well, if 90% decays, then 10% is left over, which means that I want to know what 0.1 times 2 equal to 2 times e to the negative 0.495 t will yield for a value of t. So this is 10% of initial 2 milligrams. You'll notice again here as we begin to solve for this and we divide both sides by 2, we get 0.1 is equal to e to the negative 0.495 t, which again means that it doesn't matter how much you start with, it's going to take the same amount of time to decay down to 10%, whether you start with 2 milligrams or 2 kilotons. Doesn't matter. 2 kilotons of phosphorus, though, is a lot. Anyhow, either way, we'll take the natural log of both sides, or we'll translate. The power that turns e into 0.0 or 0.1 is negative 0.495 t, or the natural log of 0.1 is negative 0.495 t, in which case the amount of time that this is going to take is the natural log of 0.1 divided by negative 0.95. Now, typically, when students first look at their answer, they tend to freak out a little bit because they think that that's going to be a negative number. It's the natural log divided by negative 0.495, and they say negative time, I must have made a mistake. But the fact is, since 0.1 is less than 1, the natural log of 0.1 is a negative number. So this is negative divided by negative, which is positive time, which is okay. In fact, this is approximately natural log of 0.1 divided by negative 0.495, which is about 4.652, or about 4.7 days to decay down to 10%.